Right. So, we excited electron from ground state to excited state, right, S0 to S1 to S2, and then let it come to S1. We looked at when it comes back from S1 to S0, it gives light, that was fluorescence. If it comes from T1 to S0, it gives another kind of light, that was phosphorescence, that we have looked at. And at the center of all the transition conceptual formalism that we had was Jablonski diagram, that's Jablonski diagram. So, that is what we have already looked at, and in the last lecture just we looked at fluorescence lifetime, time correlated single photon counting, fluorescence anisotropy, fluorescence polarization, application of anisotropy and polarization, FRET and fluorescence correlation spectroscopy. So, remember this Jablonski diagram, right, exciting electron from ground state to excited state. And when I was discussing, I did not tell you about these levels that were there, right. We told that these are vibrational level, these are the vibrational energy state, but we have not exploited this vibrational energy state. Now, when we go to FTIR, this is the level that we want to exploit it. The vibrational state that are in each electronic state, can we exploit this vibrational state as a spectroscopic measurement? So, if you look at the delta E between S0 to S1 or S0 to S2, right, it is a higher delta E between electronic state will be significant. If we talk about vibrational state, comparatively it is much lower, right. So, suppose I want to excite from here to here, I want to excite from here to here, what kind of energy you need? Thoda sa chahiye, much less than whatever I excite from here to here. So, this is the vibrational state. For exciting from here to here, what kind of radiation I was using? UV visible, right, UV visible, that means say 300 or 250 nanometer to 700, 750 nanometer. But suppose I want to excite only this, how much energy I need? Much less. So, that means H mu is much less, Hc by lambda will be much higher, lambda will be much higher. So, that is beyond red, and therefore, it is called infrared. So, to excite this state which is vibrational state, you require infrared radiation, because our energy gap is smaller. So, I want to excite only this compared to this. So, I do not need UV, I just need UV visible, I need infrared radiation, and therefore, this is called infrared spectroscopy. So, if you look at the frequency wise, we require somewhere like a smaller one, yeah, the wavelength wise it will be higher one. So, that is the infrared and vibration. So, essentially we want to excite this vibrational level rather than electronic level, and energy that is required is much smaller, lambda is much higher. So, transition between vibrational state of the ground state of molecule we are exploiting. The absorption of light happens in infrared, that is 10 to the power 3 nanometer to 10 to the power 5 nanometer, and the vibrational level of infrared generated by characteristic motion such as bending, stretching, I will come to that. So, if the molecule is bending like this, stretching like this, that creates the vibrational level, and mode of the vibration in each group is very sensitive to the chemical environment. Therefore, this is one of the deterministic technique for molecular signature, and it can be used for various functional group identification, IR. Like functional group, you remember chemistry 12th class, CO is a functional group, right, ketone is a functional group, aldehyde is a functional group, alcohol, carboxylic acid. So, FTIR is used for characterizing that functional group that is present in a molecule, and typically this functional group we cannot get it from the UV or even the fluorescence. There infrared spectroscopy becomes extremely important, right. It is a simple setup. like any other spectroscopy, you have a source of radiation. Your radiation will be IR radiation, right, infrared radiation. So, infrared comes if you heat some wire very high, then it gives you infrared. You have a monochromator, then you have a sample cell, IR source, sample cell, splitter, detector, processor and display. So, essentially that is the simple concept that you have. The only thing your source of radiation is in infrared. What is the complication of doing it? It is a fantastic tool for getting your molecular, the functional group molecular identification, that means functional group, but it is not so simple, everything comes with its own complexity. Problem is that many of your samples are in water, right. So, protein if you want to do in water, any of the biological molecule is dissolved in water. What is the concentration of your protein in water? Few hundred micromolar, ज़्यादा मेहनत की हो तो 1 millimolar. What is the concentration of water? 55.5 molar. How did you get this number? 1000 divided by 18, right? 1000 divided by 18 is 55.5 molar. So, 55.5 molar में 1 millimolar कैसे दिखेगा, right? If I want to get a signal from my protein which is 1 millimolar, you cannot get it. Therefore, doing this experiment of FTIR in water is difficult because water absorbs very intensely in the IR. So, उसका ही इतना बड़ा पीक आएगा कि बाकी सब छोटे छोटे दिखेंगे. Therefore, you have to choose another solvent or just get rid of water. So, other solvent D2O can be used, chloroform can be used, or earlier people are doing what? They are taking the protein, putting in an inert material which was called KBr, right? KBr salt, put your protein, उसको grind करो अच्छे से, make a thin film and put in the IR. So, KBr is not interfering with your protein signal, you can get a signal from protein. And so, make a dry film, dissolve your molecule in some volatile solution, place in a flat plate, allow solvent to evaporate, make a thin film and take this film, thin film in the IR radiation source, and that gives you idea of the molecule. Now, coming back to what is active in IR and what is not active, right. So, we said that it is a nice technique for getting the functional, but everything is not active in vibrational mode, right. So, if a molecule is active in the vibrational mode, we can call it IR active, if it is not, we call it IR inactive, right. So, to IR active, you remember what is happening here? We need to create some kind of vibrational mode in the molecule. Just without going to complication, suppose here is a molecule and here are two molecules like a state. So, X I will put and here also I put X. इधर भी ये बराबर फोर्स से खींच रहा है, इधर भी बराबर फोर्स से खींच रहा है. If it is pulling it like this is not, because what is happening, dipole is created but equal and opposite, it is not active, it will not be active, right. Like a CO2, but if it here, but if suppose this pulling is happening asymmetric, so electron is shifted more in the one direction, that will be IR active. So, a simple concept of the vibrational mode calculation, that how the molecules vibrates and what is IR active or not, is given by this simple concept. If the molecule has a n atoms, right, and it is linear structure, then it will have 3n minus 5 degree of vibrational mode. So, for CO2 or say H2O, how many atoms we have? 3. 3 multiplied with 3 minus 5 or 6. If it is linear, minus 5, if it is non-linear, minus 6. So, H2O is, so 9 minus 6 means it has a 3 vibrational mode. CO2 is, it will have 4. So, H2O will have 3 and the CO2 will have 4 vibrational. What are those 4 and 3? Let us look at this. So, vibrational mode, this is the equilibrium structure of your molecule. What this molecule could be? Can you sense it? CO2. This is carbon, oxygen, oxygen. Now this, how many mode we have calculated for this? 4. 3n minus 5. So one is symmetric stretching. Both are pulled symmetrically, right? That's a symmetric stretching. It could be asymmetric stretching, right? This guy is pulled, but this guy is pushed. It can be bending like a molecule is like this, it bends like this, or it goes like this, right? So these kind of bending. So that's the 4 molecule you have. Let's look at water. Water molecule has many vibrational modes, symmetric, asymmetric. Both water are pulled like this. One is pulled, one is pushed, right? It can have a rocking motion, scissoring motion, rocking to twisting motion, like a twisting, like you see ये कार का वो देखा है ना वाइपर, किसी कार में ऐसे चलता है, किसी में ऐसे चलता है. So these kind of motions we are talking about if the molecule is doing all this. So these are different vibrational mode. This rule of thumb, CO में कितने एटम है? 2. How many vibrational mode it will have? 1. केवल खींच सकते हैं, right? So these are the vibration, possible vibration mode. I am still not telling you what is IR active and what is not, but these are the possible vibrational mode that exist in a molecule, whether you are stretching or doing twisting, rocking and all those. So here is a vibrational mode of carbon dioxide. This is the equilibrium structure. Dipoles are not like a equal and opposite. So this no activity, equilibrium position. But when we have symmetric stage, this molecule is both way it is stretched, right? Again no dipole is created. This guy is not IR active, but good part is it's a Raman active. I will come to that where is the exclusivity for Raman. This, if it is a symmetric, it's a Raman inactive but IR active. Bending, it's a IR active, Raman inactive. So I will come to that what is IR and Raman effective. But to have an IR activity, you have to have asymmetric stretching, right? Not symmetric, asymmetric stretching. What about this guy? It's a diatomic molecule. It's a so HCl is एक बड़ा है एक छोटा है. It will have dipole, right? CO2 again one way stretching. So it's a IR active. So HCl and all those are IR active. CH2 group different vibrational motion it can have. Symmetric stretching, you see now you can have a video how it is symmetric stretching. Asymmetric stretching, एक pulling, एक pushing. Scissoring motion, rocking motion, right? Rock, wagging motion, एक ऊपर नीचे, and twisting motion, both are going like. So these kind of vibrational mode you can possibly see, and all of them, some of them contributes to the IR spectroscopy. So CH2, how many atoms we have? 3. 3 into 3 minus 9 minus 5. So 4. So 4 kind of possibility it has, right? Now absorption band. So this technique is almost exclusive on sample with covalent bond, and you can see this is where we get the IR spectrum. Each of this, so it gives you a fingerprint. If my molecule is like a double bond, you get here, single bond you get here, triple bond you get here, CH you get here, XH you get here. Now looking at what the functional group is, whether it is single bond, double bond, all those, we have a different region in the IR spectrum, they can come. Typically IR for some historical region, it is expressed in CM inverse, that is called not wavelength but wave number. So this is CM inverse is wave number, and typical IR spectrum comes from 400 CM inverse to 4000 CM inverse, and it gives, it's a diagnostic for a different functional group. So that's what you get in wave number and gives you idea about molecule. So depending upon what molecule you have, this kind of spectrum you get. Now here is intense OH bond, here you can have a CH bond, CO bond and different CH2 bond and all those. And therefore since they are deterministic of the functional group, we call them fingerprint spectroscopy. Fingerprint spectroscopy means You know what is fingerprint, right? You go for your fingerprint is very specific, right? The other one it will not match. So, fingerprint spectroscopy is essentially giving you molecular signature, and that is what it happens. So, there are various regions, like you can have the NH rocking, CH rocking, CC stretching, C double bond stretching, CO, and all those in different wave number that you have here, and therefore, for molecular identification infrared spectroscopy is extremely crucial. Probably I need to stop it here. Okay. So, we can stop and we can continue from here in the next class.